In modern software development, various practices and tools ensure quality, performance, reliability, continuous integration, automate the process of building and testing code to catch issues early and maintain stable releases. Dynamic analysis help evaluate software behavior during execution using tools like debuggers, memory checkers, and profilers to identify bugs and optimize performances. Techniques like fuzz testing uncover vulnerabilities by testing programs with random inputs, while debugging systematically resolves issues step by step. Performance testing addresses speeds and responsiveness challenges, ensuring software meets user expectations and system requirements. Together, these practices form a comprehensive approach to delivering efficient and secure software. Now let's discuss about the continuous integration. Continuous integration is a development process that involves building and testing the entire system regularly to make sure all the parts work well together. It helps find issues early, making it easier and faster to fix them. Imagine a team of developers working on the same app. Each developer writes their own part of the code. Without continuous integration, they would manually combine their code later, which could cause problems like bugs and conflicts because one person's change might break another's work. With continuous integration, every time a developer writes codes, it automatically added to the shared project called merging and testing using an automated system. For example, if a developer adds a new feature, the continuous integration system automatically builds into the app and runs tests to ensure nothing is broken. If there is an issue, the system immediately notifies the team so they can fix it right away. This way, continuous integration ensures the code is always up to date and working properly without relying on each developer to manually test and check everything. When setting up continuous integration, teams make decisions about how the system will be organized and tested during the release workflow. They decide how the system should be built step by step and which tests to run at different stages. A common setup includes a pre-submit test suite that checks all the codes before it is merged. This suite runs quick tests like compiling the code and testing changes that are directly affected. After the code is merged, a post-submit test suite runs more detailed tests on specific commits in the main branch, called their trunk. If these tests pass, the commits are marked as green and considered stable. Finally, a release promotion pipeline runs even more extensive tests to ensure the code is ready for release. These tests often require extra resources and check if the system is fully integrated and reliable. This approach ensures quality at every stage of development. If we talk about the automation, speed and infrastructures, it is a key to making continuous integration effective. All steps like building, testing and deploying should be automated and reliable to ensure consistency and avoid manual errors. Ideally, the process should be reproducible so the same results can be achieved every time. Speed is also important. Steps like building and testing must be fast so they don't slow down the team. To achieve this, tools like caching previous builds, skipping tests for unaffected parts of the code and running tasks in parallel can save time. Continuous integration systems should work well with the tools like version control and code review to make sure all the checks are done before merging and releasing code. A last note, good branch helps the team start new work from a stable version of code, avoiding problems in the main branch. If something breaks, continuous integration tools can track results, rerun unreliable tests automatically, and find the exact cause of the issues quickly. In a multi-system continuous integration setup, the code is spread across multiple repositories instead of being in one central place. This means the system has to combine from different repositories, which may have different versions updated at different times. It's not practical to run large integration tests for every possible combination of versions. Instead, the goal is to find specific combination of versions called configurations that are stable and suitable for further testing on release. These configurations are then tested on a large scale to ensure system works as expected. Now let's move on to the dynamic analysis. It is a method of testing and evaluating the software while it is running. It involves analyzing the behavior of the program during execution to identify bugs and performance issues. Unlike static analysis, which examines the code without running it, dynamic analysis requires the program to execute in a controlled environment. So now there are some dynamic analysis tools which help the developers to understand how their code behaves when it is running. These includes coverage tools which checks how much of the code is being tested to ensure all the parts are working properly. Debuggers which help find and fix errors in the code by allowing developers to set up through it and inspect its behavior. Memory checkers which detect issues like memory leaks or incorrect memory usage. Sanitizers which catch problems like invalid memory access, undefined behavior or data races. Profilers which analyze the program's performance to identify areas that need optimization such as slow function or excessive resource usage. Fuzz testing is a technique where a program is given random input to check how it behaves. The goal is to find issues like crashes or assertion violations that could lead to bugs or security vulnerabilities. This method became very popular in the 2010 because it is highly effective at uncovering security flaws. Advanced methods like genetic algorithms or neural network can also be used to generate inputs that specifically target certain parts of the program, helping to identify issues in less commonly tested areas. In performance testing, we face several challenges that make it difficult to measure and improve system performance effectively. One key question is determining how much improvement is possible. Tools like Amthel's law help identify limits to speed up from parallelization and local optimizations. Another challenge is identifying whether slowdowns are isolated to specific parts of the system or caused by complex interactions. Reliable measurements can also be tricky due to factors like inconsistencies, system load, just-in-time compilation, or intuitive testing tools. Testing needs to consider both average performance and worst case scenarios. Additionally, there is often a trade off between reducing response time and increasing data capacity. Addressing these challenges require careful planning, realistic dataset, and appropriate testing tools. Thank you for watching, and I hope this helps you in your software development journey.